All right, thanks, Candice. Hello, everyone. I'm really happy to be here. My name is Andrea Righi. I'm a kernel engineer working at NVIDIA. And let me switch to the slides, actually. Okay. I hope everyone can see the slides. Yeah, we're going to be talking about scheduling today. Uh, so the scope of this webinar is to guide you in this technology called SCADX. Uh, I'm going to be starting with a little bit of theory about scheduling, also just so that we can get more familiar with the topic. There's also, I want to mention that there's a talk by David Vernet at Kernel Recipes that is introducing SCADX and how to design your schedulers. It's like 2 years ago, more or less. But since then, a lot of things have been changed. So yeah, I took this as an opportunity to like do an updated talk in general about scheduling and specifically in SCADX. Now you can use this technology to do your own experiments. Um, Here's the agenda. We will start with some scheduling generic concept. Then we are going to move to the SCADX uh, API and how you can use that to do your experiments, and some hands-on. Like Candice said, feel free to ask questions. I'll try to keep an eye on the chat. See some familiar names there. And yeah, we're gonna be switching between slides and demos. So everything is supposed to be interactive. Hopefully not too boring. We will see some demos as well. And the expectation, well, I would like you to become familiar with SCADX just by watching this webinar, but I understand it's a very ambitious goal. So at least I hope I can give you some curiosities or you can see some concept and that you can use it and do your own scheduling experiments and potentially being able to craft your own scheduler. Um, all right. So let's start with about schedule. But I want to do something different this time. Usually I start with the whole introduction and then we move to the demo. I actually want to start with the demo and then we see what happens and then we try to understand why it happens and how we can fix that. So let me switch here. I hope you can see. Let me move myself down here so you can see the core utilization. Okay, I hope you guys can see. If you're wondering, I'm using a distro called CacheOS, which is basically an Arch distro, but they have a kernel with, well, now the SCADX is upstream, so all the distro are slowly supporting that. But I want to give a big shout out to CacheOS because they helped us a lot, and they keep helping us by testing the schedulers, and so that's why I'm using this distribution, which is also really nice, by the way. And SCADX is very well integrated in this distro. Okay, so let's start with a game. This is Terraria. It's a cool game. You walk around, you build things, kill monsters. Let's see. Can you see the frame rate down here? I hope so. Say in chat yes if you see the frame rate.
Yes, we can.
It's
Yeah.
okay. Now that was just to force people to be interactive. Anyway, yeah. So it's going 60 FPS. That means it's good because if a game goes at 60 FPS, it means that the human eye is not totally correct, but we can model the human eye as a device that is sampling at 60 FPS. So I perceive the game being fluid and nice to play. Now, what happens if for example, if I start a kernel build? So now I'm building the kernel in the background while playing the game. You can see up here that the core utilization went like all the way to 100%. All the cores are busy. And if I go back to the game, yeah, you see like it's quite laggy. That's what like gamers call lag. It's very I mean, it's a strong lag because I jumped from 60 FPS, now I'm going at 25, 20. And it's even worse than that because I'm like, it's not 20 and consistently stable. It's low and also like very unpredictable. This gives a very bad gaming experience because it's like you see my characters are speeding up and then slowing down. So let's see. What if I load a different scheduler? That's what SCADX allows you to do. You can load a different scheduler implemented as a BPF program while your system is running. So I'm running another scheduler. Now there's another scheduler that is running, and my game is now going pretty smooth. 60 FPS again, I can play the game. Core utilization is still 100% everywhere. So the kernel is still building, the game is going, and apparently I can do both at the same time. So that's a lot better. If I stop this scheduler and everything falls back into the default Linux scheduler, and we're back to like, 17, 20 FPS and stuff like that. So let's stop this, go back to the slide. Okay, we have a scheduling problem, right? Apparently. And why is it happening? And how can we fix that? So far, do you have any questions? I mean, lots of questions because I haven't said anything. I just showed the demo. But yeah, I think that the problem is clear. Like it's kind of an extreme problem because gamers are not building the kernel while playing the game. But this is just to highlight that there are certain use cases that can be improved a lot. Does this tool works in any distro, Mario? So it's like it's merged upstream in 6.12. So any distro that is shipping a kernel with 6.12 should have SCADX enabled, meaning that you have the kernel component that allows you to write schedulers and load them. Then, of course, you need like user space schedulers, either pre-compiled or you can compile on your own. Everything is open source, of course. The distro that I'm using, CacheOS, already supports that since 6.8, I think. But Ubuntu will have that in 25.04. So in Ubuntu Plaki, we'll have SCADX enabled. Ubuntu SUSE Tumbleweed already has a kernel with SCADX. And also Red Hat is, I don't know the timing, but they're obviously moving. As soon as distro will have a 6.12 kernel, you will have this tool. Okay, cool. So scheduling, let's define what scheduling is, because again, we say that, okay, this is a scheduling problem. But what does the scheduling do? Was this problem not seen earlier? If so, was there an attempt to solve this earlier? Well, it's like, we'll get that. We'll get there. I'll explain why we see this problem. Piotr, as you mentioned in our conversation, you can't make a scheduler that will satisfy everyone. Exactly, that's exactly the point. And it's where I'm going. So let's define a scheduler. A scheduler is a kernel component that determines where each task needs to run, when, and for how long. So that means, video is blurry. You guys see the slides? Okay. Basically, you can see the scheduler as a component that is doing CPU allocation and time allocation. So you need to determine like each task where you want it to run and for how long and in which order. It seems easy conceptually, but in practice, it can get really complicated. Like scheduling is a really non-trivial problem. There are many corner cases. The goals for a scheduler is to be fair. Like all the tasks should receive at some point some CPU time. You don't want tasks to be stalled forever or indefinitely. So everyone should get a chance to go. You also need to make optimization decisions. Like let's say usually you want to keep tasks running on the same CPU as much as possible because of cache locality, right? Or at least you want to keep them in the cores that are sharing some caches, or in the cores that are in the same NUMA node in case you have more complex topologies. So these optimal decisions need to be considered when you design a scheduler. Otherwise, you don't have, you're not using your system with the best performance. In doing so, the scheduler also needs to be, let's say, it needs to react fast, so low overhead. That doesn't mean that the scheduler itself is computationally intensive. Actually, quite the opposite. The scheduler should run in small CPU bursts and determine who goes next as fast as possible. The reason is that, like, usually if you look at the CPU load, you should see, like, if you see 100% CPU time busy, it's a positive sign if this 100% CPU time is mostly user space time and not the scheduler itself. Because if your scheduler is hogging a CPU, let's say, well, it's not working really well. Like, you add too much overhead in that. And the last one, actually, let me move up here. So the last point, the generalization, is basically the topic of of this talk. The thing is, like, the scheduler should work on all architectures and for every workload. A good scheduler needs to make everyone happy. And it's very difficult to model a scheduler that works everywhere and for everyone. Sorry, I was reading chat. The video looks clear. Okay, cool. Thanks, Candice.
So there is a question in the Q&A, Andre. Is this program similar to cron, or are we talking about something different? I'm not sure which program, Mario. What are you referring to, I guess? That's
similar to what? Cron, huh?
Cron job.
Yeah. Oh, cron. Oh, okay. Okay, let me open the Q&A.
Yeah, Q&A.
This program similar to cron. I have to say that I'm not familiar. What do you mean? The only cron that I know is the cron job.
Me too.
Thing that you spawn tasks at a certain time.
Yeah, hopefully Mario will come back and tell us.
Mario, if you have more, ask in chat maybe. Oh yeah, that's what I referred. So cron is with cron you can start jobs or tasks, let's say, at a certain time, but you're not actually prioritizing or deprioritizing certain workloads. It's kind of a different. Cron is not. You can see cron as a scheduler more or less, but it's more of a management tool, like when you need to automate some commands and so on. What cron can't do is, like, you have a bunch of tasks running in the system competing to get the CPUs. How do you assign them? How do you assign these tasks to the CPUs, and how do you determine in which order they run, and how much time do you assign for each task? So you can see like a cron, but that's cron is much more simple than that.
Yeah, cron is more like a series of tasks you want to do at a certain time, and then you can kick them off automatically and set them up. Say maybe you want to turn lights on at some point.
Exactly.
Or something like that. So there are a few questions in the chat. Looks like.
I missed that.
Yeah, we'll schedule.
Go ahead.
Right after the video blurry one from Devender, will SCEDEX overpower default scheduler?
Okay, no, I think we still need a default scheduler, and like I say, generalization here. That's the key word. Like, the default scheduler needs to be as generic as possible. We need to have a scheduler by default that makes, like, all the possible compromises to make everyone, how to say, not too unhappy. So yeah, it won't make everyone happy, but at least it would make everyone not too unhappy. And in fact, let me get to the next slide. So that's about the scheduling in Linux. So the policy in Linux is to have one scheduler to rule them all. Over the past years, we had many proposals to like have a pluggable scheduler interface or have multiple schedulers. It has been always rejected, this idea, for valid reasons. One of them is like it used to be a performance, like you don't want to add artifacts and whatnot to the like the scheduler code should be considered like entirely a hot path in the kernel. So the least amount of logic that you put there, the best. But the other reason, which I think was more relevant, is the fact that like if we have a single scheduler, we're kind of like all the kernel developers are forced to join forces to make possibly the best scheduler, and that was the reason. However, like this happened, yeah, a long time ago. Like if you look at this slide, for example, so we used to have CFS, the completely fair share scheduler, before 6.6. After 6.6, the scheduler changed to EVDF, which is a deadline-based scheduler. And CFS has been working like for 15 years, and it was fine. But systems were much simpler at that time. We didn't have, Linux was running everywhere, but we didn't have a pool of heterogeneous workloads like we have nowadays, especially considering that nowadays Linux run on desktops as well, or in mobile phone, like it's running this phone. It runs in HPC systems. In the past, Linux used to be more like of a server system for servers. Nowadays, it's more like in our everyday life, also in end users' devices. Gaming on Linux is becoming a thing. So on one side, we have more requirements to differentiate the workloads that we have and the typical usage of Linux. And on the other side, we have more complex architectures. Like we have the complex dies nowadays that have like heterogeneous cores inside the same package. So you have, for example, big little or E cores and P cores. We have in the same system, the same package, we have cores optimized for performance and cores optimized for energy efficiency. So if you decide, one task goes here, it may change the performance and power consumption. So the logic that the scheduler needs to handle is much more complicated. And that was the main motivation over why SCADX at some point was proposed. Also because, like I mentioned in this slide, it's really difficult to conduct experiment, and it's really difficult to upstream changes. The experiment part, yeah, of course, because if you change something in the scheduler, you need to recompile the kernel, you need to reboot. It's not something that you can do in production most of the time because it's risky. And also because sometimes rebooting a system, like in large cloud environments, if you reboot a system, you need to rewarm all the caches, and it's a very expensive operation. And the second part, like it's difficult to upstream changes, means that, again, generalization, what I said earlier, the scheduler needs to be, as generic as possible. You can't regress the scheduler. If you find something that works really well for you, but doesn't work for everyone, it won't get merged. So these are like very hard constraints. So that these two things make scheduling development really difficult, quite unapproachable, unless you have a lot of years of experience, and again, you are kind of limited in what you can do. So that's why SCADX was proposed. And finally, like in 6.12, it was merged. So now we can implement scheduling policies as BPF programs. And the things like the key features is like, okay, you can design custom schedulers like the one that I showed earlier that is not, like, to answer the question, like it's not better than EVDF, which is the default scheduler. It's not better in general. It's better for that particular use case. So the key is like specialization. That's one of the big important features that SCADAX brings. The other one, which is my personal favorite, is rapid experimentation, because having the possibility to basically reprogram the kernel, like not sure if you're familiar with BPF, but BPF is basically a JIT in the kernel. You can see a BPF program as a kernel module that cannot crash the kernel. So it runs in a safe sandbox, and you have access to all the, like you have read access to everything in the kernel. And with SCADAX, you can take scheduling decisions in your BPF program. That means you can load the program and see how things go. Yeah, it won't crash your system, because if there's any like access that you're accessing some memory areas that you're not supposed to access, or if you do something wrong, there's a verifier. It won't, and the verifier won't load your program. Or if you're stalling a task, or if you're introduce a kind of starvation or deadlock, like runtime problems, the SCADAX core implements a watchdog. So if any task is not scheduled for a certain amount of time, which is configurable, the SCADAX core, the in-kernel core, will kick out your scheduler and transparently migrate all the tasks back to the default scheduler. I think this is really powerful, because you can literally do tests. Usually in kernel development, you have a very long turnaround between a test and another. You edit, compile, test. Usually in user space, you do edit, compile, test, edit, compile, test, edit, compile, test really rapidly. You don't have this in the kernel. And with SCADAX, you can have this workflow, with this rapid workflow. And so like that, I think that's probably the most useful feature that this technology brings on the table. So that was a long answer to the question, but we'll keep going. Let me see if there's any other question. Scheduler
there are a few more questions. Yeah.
Okay. Are you going to? Okay. Yes. If you.
So if you're looking for a marker, that would be, does running the scheduler as a BPF program cause overhead versus no BPF?
Let's see. I was looking for the. Can you repeat the question, Shua?
Yes. Yeah. Does running the scheduler as a BPF program cause overhead versus running it without BPF? I think that's the question.
Okay, the overhead. So yeah, that intuitively we are tempted to say yes, BPF, of course, there's an extra layer, so it's going to add overhead. But again, as I mentioned earlier, first of all, the scheduler is not a CPU intensive job. It needs to react fast. That's the only requirement. And in addition to that, BPF code is actually kernel code. You can literally see a BPF program as a kernel module, because even if it's compiled in a BPF bytecode, when it's loaded, there's a JIT, so it's just-in-time compiler. So the bytecode is translated into like machine instructions. So it's like running kernel code. And for this reason, like, there's basically no overhead. We have we've done a lot of tests and measurements, and like even doing simple things like the FIFO scheduler compared to SCAD FIFO in kernel, there's no difference basically. Actually, sometimes the BPF1 runs faster, but that's just because of the a slightly different policy of allocating CPUs, and because it's simpler than the one in the kernel. That's the reason.
So this another question is, are you going to compare pros and cons of SCADAX XT with the current one in the kernel? Default scheduler.
Compare pros and cons of SCADAX with the current one in kernel. Yeah, so the thing is, like, we have already many SCADAX schedulers, and we often run some comparison and benchmarks. Of course, there are use cases where specialized schedulers like completely overperform, like completely beat the default scheduler just because we can relax certain constraints, like the demo that I showed earlier, where like you have a video game with some background load, that like the SCADX scheduler destroys the the default scheduler. So it's in general, again, the best scheduler, the best generic scheduler is EVDF in general. But then there are many use cases where you can speed up your performance a lot by using a custom scheduler. And because the default scheduler needs to be generic, if you have a very specific workload or a very specific architecture and you're interested only in your use case, I mean, there's so many low-hanging fruits that you can easily outperform the default scheduler because you can be less defensive, you can relax constraints, let's say you don't care about fairness, you win automatically. It's really easy to design a scheduler that outperform the default one.
There is one more question. Are there objective methods to evaluate whether our custom scheduling policy is effectively meeting its goals?
So that's an interesting question. We're currently working. Something that we are lacking is more tooling to trace what's happening, and also at some point we define, like we say, we need to define a subset of benchmarks to measure like the goodness of a scheduler in general. Like we have schedulers that are we have schedulers in SCADX that are quite specific for specific workloads. Like we have SCXLAVD, for example, designed by Chenggu Min at Gallia. That scheduler is specifically designed for the Steam Deck, and soon, at some point, the Steam Deck will, when the Valve will move into 6.12 kernel, will use a SCADX scheduler instead of the default one, just because a specialized scheduler, the design for gaming also works better for that particular scenario. In that particular scenario, we also have generic schedulers, like BPF-land is a scheduler that I maintain, is generic enough, is supposed to be used for desktop usage. It's actually the scheduler that I'm running right now to do this live this video because it gives better priority to latency sensitive workloads. So like live streaming, for example, it works pretty well. So again, but it would be nice to do a comparison in general. I've done some generic comparison, and again, there are some use cases where the default scheduler beats BPF-land. There are other cases where BPF-land beats the default scheduler. So it depends.
There are 3 questions in the Q&A and also another question in the chat. Would you like to delay them or would you like to take them now? It depends on.
No, it's fine. It's fine. Okay. It's fine.
Okay. So let's go to the chat then. If you were looking at it, do SCADX EXT BPF programs have access to all metrics? And I think maybe you can read that
exactly.
question.
Yeah, that's a good question. I actually have a slide about it. Let me jump to I'll just speed up and we go to the slide because it's fine. I mean, we don't have to go in order. So this is one interesting thing that you can do with SCADX is the fact that, so you have a user space program that is loading the BPF bytecode and is injecting the bytecode into the kernel using the BPF syscall. So but the user space program remains live. It's what keeps the BPF program alive. And one really cool feature is that the BPF program shares the address space with the user space program. So as you know, there are BPF maps that can be used to communicate efficiently between kernel space and or BPF space and user space. There are also like ring buffers, the BPF ring buffers that are also lockless, by the way. So you don't have like, and you're not using syscalls. It's like direct access. And those are very efficient. And you can use those to communicate information, pass information between BPF and user space. That means you can do two things. One thing, you can offload some complexity from BPF to user space. For example, we have a scheduler called SCX Rusty, written by David Vernet. This scheduler is implementing like all the auth paths and all the scheduling logic in BPF. And it's implementing a load balancer. The load balancer is the component that decides like, okay, we have a scheduling domain that is too much overloaded. Let's migrate some tasks on another scheduling domain. That's the load balancer. And the SCX Rust implements the load balancer in user space. And it's written in Rust. And it's communicating using BPF maps. And we have seen that like this approach is the most successful, like when you have like the hot paths implemented in BPF and like move complexity to user space and use maps to communicate. Because like, first of all, you don't have like you can use like all the user space libraries. You have access to a lot of libraries that you wouldn't be able to use in the kernel or in BPF. You also unlock the possibility to use any language. So another cool project is called SCX Rustland, which is it's a framework on top of SCADX, and it's this slide basically. So it uses it implements a minimal BPF scheduler. It's not like a scheduler; it's more like a little framework that passes everything to libBPF, and libBPF RS is the Rust binding to libBPF. So what it does is intercepts all the scheduling events in BPF, passes everything into user space task using BPF ring buffers. It's taking 100% of the scheduling decisions in user space and sending the result of the scheduling back to BPF, and BPF sends the results to SCADX. So what happens is you have a user space process that is scheduling all the other tasks in the system, itself included. So it's a scheduling that schedules itself as well. That's actually a good entry point if you're interested to, like, if you don't have much experience, it would be a good entry point to start doing experiments with scheduling, because you can create a scheduler just by, cargoing it, and you import a crate, the Rustland crate, and you're done. You implement like there's a few APIs. I also made a video to show like how easy it is to implement a scheduler using Rustland. And the video shows like I'm actually asking ChatGPT to, like, I give the Rust crate documentation and I ask ChatGPT to implement a scheduler. And I literally like download the response from ChatGPT and compile and I run the scheduler, like literally, like it's really easy. So yeah, that's something that works really well. You can do this and to unlock also other more complex functionalities that you wouldn't be able to implement easily in the kernel, or especially in BPF. BPF is even worse because your programming model is also limited. Like you can't have allocations, you can't have unlimited cycles. You also have all the usual kernel limitations like the stack size. You can't use floating pointers and yada yada, a lot of other things. Oh, let's see. Let's go driven by questions, because I guess like I have other slides for other questions. Does SCADA? I remember testing the scheduler from ChatGPT. It worked quite decently, Piotr. Yeah, I mean, it's not, of course, the result is not as good as writing. I mean, we are far from having an AI designing a good scheduler. We're not quite there yet, but it's surprising that something considered like totally inaccessible as writing a kernel scheduler for Linux can be done simply as a result of asking. And I wasn't asking anything technical. I was like, please design a scheduler, a deadline-based scheduler using this API. And that was it. But who knows, in the future, we may have like scheduler design by an AI, not now. One thing that it would be nice to explore, I think, is collect traces, like profile a system, and based on the trace, try to generate a scheduler chart. Try to guess what kind of workload you have, and based on that, automatically generate a scheduler, and use KDX to load that in runtime, see how it goes, or maybe iterate, test more schedulers, do more change, keep collecting traces. That's probably something that might work in some cases. Right, let's go back to where we were. I have some math here that I'm afraid I need to explain because that's part of the presentation. So fairness. Unless we want to, unless there's a question about that, maybe.
So there are several questions.
Let me finish this one.
Okay. There are several questions in Q&A when you
let me finish this one.
Okay.
Perfect. We do this. We cover this one, and then we have covered all the theory, and then we can do questions or even tests. So I want to mention about. So this equation. This is what drives most schedulers, at least in Linux. This is the concept of fairness. When I mentioned like a few slides before, yeah, CFS, the completely fair scheduler. What does it mean? So fairness. It's basically how you can do bandwidth allocation, fair bandwidth allocation with CPUs. It's a proportional weight-based CPU allocation logic. Let's say, so each task, it seems complicated, but it's not. It's very intuitive. Basically, what you want to do, each task has a weight that, of course, is derived from the priority. So each task has a weight, and you want to assign runtime proportional to the weight relative to the weight of the other tasks. So there's an integral here, but let's assume the weights are constant. So this one becomes like the weight of a task. So let's say we have a time interval, T1 minus T0. And a task I has a weight of Wi. You divide its weight by the sum of the other weights of the tasks that are running. And then you multiply by the time interval. So basically what we're doing, we are dividing the time across running the tasks that are competing the CPU proportionally to their weight. So let's say, we have two tasks, both have the same weight, 1 and 1. If you replace these values to the formula, we get that, one task gets 50% of the time interval, the other one gets 50%. Is intuitive, right? That's what I want. I want to, do two tasks with the same weight. I should get half of the CPU equally. Now, let's say we have, again, two tasks. One of them has a weight of 3. The other has a weight of 1. Now I do the math again. And yeah, one task gets 75% and the other one gets 25 because its weight is 3 times the other one. So it's relative. And of course, you don't want the task that has more weight to always override the other one. Otherwise, the other one would just starve and stall forever. But this is the most elegant solution, the most generic solution to provide fairness. In this way, everyone will get a chance to run, and their amount of time will be proportional to their weight. And how you implement this? You implement this with a vruntime or virtual runtime. And I wanted to mention this because if you read the documentation, the SCADX documentation, it's mentioned a lot of time, and sometimes people are like struggling, like what's vruntime, what's virtual runtime? So it's this one. It's an implementation of this formula, and you implement the vruntime by doing defining a baseline weight that traditionally is 100. You divide the base weight by the task weight, and you multiply by the actual runtime of the task, and you account this time to the task. And every scheduling tick, you pick the task with the smallest vruntime. So let's say a task that is sleeping all the time will have a small vruntime and will get more chances to run. A task that is running all the time constantly will get a higher vruntime, so it has less chances to run. But this is exactly what we're doing here, right? It's like prioritizing, giving a time interval proportionally to tasks, also considering the weight. So this is how this vruntime formula is how CFS was implemented. What the scheduler that we used for 15 years in Linux was based on this logic. And what's the problem? So, okay, hold on. What's the problem here? The problem is that it's super generic. It works mostly every single time. But the downside is that it's not really good for latency, because let's say, okay, one example, you have a lot of tasks that are sleeping, and you have one task that is running, but it's kind of periodic, like, I don't know, an interface, whatever, or a video game. Now, all the tasks, like you have, let's say, 100 tasks that were sleeping, they have a small vruntime. They all decide to run at the same time. Well, they will get the CPU before the other task that was running before, because we care about fairness. But that would impact on the latency sensitive task, because they will get a chance to run before the latency sensitive task. So we had to come up with some ad hoc solutions and workarounds and special logic to make latency sensitive tasks not deprioritized by this logic. You can play with weights and priorities, but it's always difficult to find something very generic. So that's why at some point we had EVDF. EVDF is still fair because it's using a deadline that is the formula right here. So EVDF is assigning a deadline to each task that is based on the vruntime, this one, that is the same as the CFS, plus a proportional time, a time that the task is requesting, scaled by its weight. So that means, let's say I am a latency sensitive task. As a latency sensitive task, usually I can request like a small amount of CPU and then release the CPU immediately. That means my delta T here is really small. So my deadline will be smaller than others that request more time, and I get more chances to run. So this allows to order task by deadline, not by vruntime, even if there's still a vruntime component that gives me fairness. But in addition to that, I can prioritize tasks that are requesting a small amount of CPU time. And in addition to that, but again, this works for prioritizing latency sensitive tasks, but at the same time, I want to be fair. I still need to guarantee fairness because this is the scheduler. There's only one. So I want to be able to provide fairness. So that's why EVDF, that stands for Earliest Eligible Virtual Deadline First, introduced also the concept of eligibility to mitigate the fact that the potential like breakage of fairness that you may have using a deadline. And how you mitigate? Basically, you get the earliest deadline among the tasks that are eligible. And the tasks that are eligible are those that have a lag, and then we define lag, that is great, that is not negative. So a lag is so this is not the definition of the paper, but it's how it's implemented. But you can see the lag as the ideal time that a task should get minus the time that it actually got. So, if I got less time than what I'm supposed to have gotten, I would have a lag greater than 0, and I am eligible to run. So if my deadline is the smallest one, I will be first to run. But if my lag is negative, it means that I've used more time than what I was supposed to use according to the perfectly fair logic. So I'm basically delayed. I won't be eligible to be scheduled. Okay, this is okay. You don't have to understand everything, all the little details of this, but the idea is EVDF is still fair, it's still completely fair, but it also allows latency sensitive tasks to win in a short time frame. And over the time, if some task abuse the deadline logic, they would still slow down by the lag. So basically, it's fair, but at the same time, it gives better chances to run to latency sensitive tasks, which is cool because it's like the idea, the goal, that the problem that we were trying to solve was the latency, like being able, making Linux more responsive, and it solved the problem. That's it. And at the same time, it still provides fairness, but that's very good as a generic approach. But again, sometimes you don't care about fairness. Like you can accept to, you can relax the fairness constraint to get better latency performance. That's what I'm doing with the scheduler that we saw earlier with the video game. The scheduler before is just using a deadline and it doesn't implement the lag. It's more or less kind of an EVDF without the eligibility. It's using also different formula for the deadline, and if there's time we can see. But the idea is like I'm completely relaxing the constraint of being fair so that I can get better performance for latency sensitive tasks, even over a longer period of times, which is something that the default scheduler can't afford because it needs to work well also in the servers. It needs to work well in many other scenarios. And it would be not acceptable to make a change like I did in my SCADX scheduler and apply that upstream, because it wouldn't work in some cases. It would regress other workloads, but it's possible using SCADX. So that's the theory part, so we can get other questions. Let me see. Let me go to the Q&A.
Yeah, that's where a lot of questions are.
Oh, wow. Yeah. Well, that's fine. At least I finished my theory part of like, yeah.
Good timing then.
Yeah. So, okay, I'm going in order. Is that okay in the Q&A?
Yeah, please.
Okay.
Yeah.
So what community scheduler would you recommend for a network-heavy multiplayer gamer? So gamers, okay, thinking of Marvel Rivals, CSGO, Dota 2. So CSGO is actually a good benchmark, a good gaming benchmark, because it's really difficult to make this. It's very susceptible to background workloads, like the FPS drops significantly as soon as you start something in the background. So there are two schedulers three schedulers in the STX repo. So we have SCADX is like there's the kernel part, and we also have an STX, a repo called STX, where we implement the actual BPF schedulers. And we have three schedulers that are probably suitable for gaming. The obvious one is LAVD, written by Changgu Min from Igalia. That scheduler is designed for the Steam Deck, but it also performs really well in other architectures. Like it doesn't have any strict requirement on the architecture. And in short, what this scheduler is doing is detecting pipelines, like wakers and wakey relationships, and it's keeping track of the frequency, like how often a task is blocked and how often a task is awakened, stuff like that. Because if you think about a game is like a big pipeline. There's a main loop that waits for a frame. Then there's a scene manager that updates the scene. Then the new frame is passed to the compositor, and maybe there's Wayland that is rendering the frame in the video, and then everything goes back to the beginning. And it's very cyclic. Like you need to do that every, if you're playing a 60 FPS, you need to do that every 1/60 second, which is like every 16 milliseconds. You need to do that periodically. And if you miss the deadline, you perceive the lag. So by detecting this chain of pipeline, it seems to be very effective to prioritize gaming workload over everything else. And again, the example that I showed at the beginning with me playing Terraria while building the kernel, of course, is an extreme example, but usually those schedulers are what we care about is like the P99 FPS, right? You want to, especially in e-gaming, or if there's a kind of some competition, you may want to guarantee like a good proper level of performance, even if, let's say, I don't know, an update is started in background, or something is like to mention cron earlier, cron decides to run something, I don't know. Even in that case, you may want to provide a good quality of service for the latency sensitive workload, in this case, the game. But it's not only that. If you think about VR headsets, for example, or complex wearable devices, all these devices have many threads, many tasks, which are, in theory, they're all real time. So it would be really difficult. Like you have, telemetry, you have cameras. Like if you think at the Oculus, for example, you have cameras, telemetry, accelerators, many threads that are collecting information, and there's also the game itself. So playing with priorities on C or C groups can be really, really tricky. So that's why, like, being able to implement a scheduling policy that automatically understands and is like automatically figures out who needs the best priority at every single time. That's very powerful. Like, there's a great potential in that, especially in gaming. I actually think like SCADX can do something significant to promote gaming on Linux. So yeah, sorry, to answer the question, network heavy multiplayer gamer, I would say LAVD or BPF LAN, maybe Rusty as well, but BPF LAN and LAVD are probably the best two, because they prioritize latency workload in different ways. And in network is also latency, network intensive multiplayer gaming workload is still latency sensitive, because it's not like a backup over the network, right? You care about the ping, you care about the response time, especially if you're doing like competitive gaming. That was John Wyatt. Then we have Christina. Does KDEX support clock-driven, time-driven scheduling implementation? Yes, you can. So the cool thing about SCADX is that a scheduler is a BPF program. So you can do anything that you usually do in BPF. And in addition, you have the scheduling callbacks that you can implement to actually implement a scheduler. So you can use BPF timers to trigger certain events on a time-based logic. You can also, for example, a really effective thing that you can do, you can add K-probes. So LAVD, for example, or BPF, actually, we have another scheduler that is called Flash. Both Flash and LAVD are actually adding K-probes to the Futex kernel calls to determine when a user space task is holding a user space lock. And it boosts the priority, like it allows the task to keep running even if its time slice is expired, if it's holding a user space lock. That's really like it's really powerful, because you can like kind of prevent priority inversion for user space locks, which is kind of cool. Like, and you don't have to introduce any new kernel interface because everything can go through BPF, and BPF is just a pure kernel to kernel interface. You don't have UAPI restrictions, right? So usually it's complicated to introduce new kernel interfaces because then you need to maintain them forever because of the UAPI restrictions. And in this case, instead, you're like it's like a kernel module. So yeah, you can and you have a way to efficiently communicate between kernel and user space, like we mentioned earlier. But yeah, to answer your question, yeah, you can do clock-driven, time-driven scheduling implementations via BPF BPF timer. Sorry. Next one. For those of us who are less familiar with schedulers, are there pre-built options that we could use for testing with SCADX instead of having to write our own? Yes, of course. Like I mentioned CacheOS as a distro. Well, maybe I can show that. For example, so this is CacheOS. Let me go here. Oops, sorry. CacheOS has a tool that is called CacheOS Kernel Manager. That you can use like if you want to recompile your own kernel and whatnot. But there's also this SCADX scheduler config. And if you go here, like you see like there's a pool of schedulers. These are like the upstream schedulers that we have in the SCX repo, some of them, not all of them. And you can just, you can literally pick any of them, like LAVD, and I click apply. Yeah, I need to put my password, of course. And now I'm running LAVD. So now I have a different scheduler, which is also good for gaming, this one. Or I don't know, I pick BPF land. And you see there's also a pool of profiles. So let's say I want gaming. I want to run BPF land with the gaming profile. And it shows here the options that you need to pass to BPF land to use this profile. Then you click apply. Yeah, my password again. And now I'm running BPF land. And if I do disable, now I'm back to the default scheduler. So this one is really easy if you want to do experimentation. Like you don't have to do anything basically. You don't have to write your own scheduler. Yeah, or otherwise you can compile them and run them manually, like I was doing earlier. Next one. Let me see. Run SCX systemctl SCX loader to. Okay, yes. So SCX loader is a user space component that CacheOS, for example, is using to load all the different schedulers. So we have this kind of manager of schedulers that is, yeah, that's kind of cool. Let's see, next question. Are you suggesting custom schedulers for specific domains and applications which are known, advanced? Schedulers for specific, yeah, I mean, well, yeah, that's the point. Like scheduling specialization is the whole point of SCADX. I mean, one of the biggest point of SCADX. The other one is, of course, experimentation. And sometimes we may find something that works really well in general, and we may decide like if it works in general and if it's better than what we have, we can upstream that. So another important use case for SCADX is also, of course, experimentation and being able to use that as a new tool to improve the in-kernel scheduler. So there's this one that, like, joining forces to do more experiments, open scheduling development to a broader, wider range of programmers and developers, and then at the same time giving the possibility for people to use different schedulers for different domains of applications. Does SCADX offer support for real-time scheduling? So yeah, that's a good question. You can use SCADX with preemptor T. So real time is a thing. Scheduling is another thing. So real time is, they're connected, but real time is more about predictability. So it involves, there's a lot of code involving locks, changing locks and the semantic of locks. Because you're not supposed to, you're always supposed to be able to sleep. And in addition to that, of course, we may have scheduling requirements to guarantee the predictability. We have sched deadline, for example, in the kernel, which is not a schedx. It's a separate schedx class. I actually have a slides with this. Yeah, so this is, when I say Linux as just one scheduler, that's not completely true. We have one scheduler for non-real-time tasks. That would be more correct, because we have real-time schedulers already in Linux outside of schedx. Here's the ranking of scheduling classes. The problem is that a higher scheduling class can completely override a lower scheduling class. So let's say you have a sched FIFO task running on a CPU. If it's spinning on that CPU, it would completely hog the CPU. So sched normal, schedx, of course, sched idle, they can't run on that CPU if there's a sched FIFO that is running. So there's this ranking of scheduling classes, and it makes sense because the goal was to provide real time, which is supposed to always override sched fair, like the normal or batch. And as you can see here in this slide, schedx runs below sched fair. So this is important. Usually we allow, so by default, if you load the schedx schedulers, all the sched normal and sched batch tasks are moved into the schedx class. But there's a possibility to use a partial mode, which is it's called partial mode, where nothing is moved automatically unless you explicitly move them into schedx. So you can also have a system that is only scheduling a subset of tasks using the schedx, the scheduler, your BPF program. And all the other tasks will be still scheduled by the default Linux scheduler, the fair class, so EVDF. However, we never recommend doing that unless you know exactly what you're doing, because of this slide. That means if you run in partial mode, any task here in sched normal can completely hog a CPU and never get the schedx scheduler any chance to run. So it's kind of, I mean, I don't want to say dangerous, because worst case is that, you know, a task would be stalled for schedx. The watchdog in kernel would detect that a task didn't get the chance to run for a certain amount of time, and it would just kick out your schedx scheduler. So you won't be able to disrupt the system. Worst case scenario, you would perceive like a stall until the watchdog kicks your scheduler, and then everything will be back to normal. But you know, it's good to know that if you opt for the partial mode, you may hit this problem. We also have this problem, like people, if there are people from the CacheUS community here, they're familiar with the kthread stall. We had so many issues with the kthread stall, which usually is not a schedx problem. For example, if there's a sched FIFO task that is running on a CPU, of course, schedx would be completely starved and stalled by the sched FIFO task. Oops, sorry. So what happens is the watchdog would detect like, oh, hey, you didn't schedule a task on this CPU for a certain amount of time, but that's because there was a real-time task running on that. So the watchdog, just to play safe, it would kick out your scheduler, triggering a stall, and you see the stall. I actually have a stall in a slide. Let me go there. Exactly, this one. So if you see, so when your scheduler exits, it would dump a trace that you can inspect to see what happened. In this case, there was a kworker /6 So a property of this kernel thread is that it can only run on CPU 6. Like if you try to dispatch this on a different CPU, you can't for kernel requirements. However, in CPU 6, there was a task called yes. You know what yes does? It's just print yes, forever. So it was, I intentionally created a CPU hog running as sched sched FIFO, sorry. So in the real-time scheduling class, that was hogging the CPU. So this guy that was managed by SCHEDX didn't get the chance to run for 7 seconds even. And so SCHEDX detects that and would kick out your scheduler, even if in this case it didn't solve anything, because there was still the real-time task, like what, and you can't do anything because it's a higher priority scheduling class. So yeah, real time, again, real time is tricky. And also keep this in mind. Like where's the, yeah, keep this in mind when you see some stalls, if you decide to play with SCHEDX. Two things that I want to mention, and then we dedicate time for other questions, is the concept of dispatch queue. This is how SCHEDX is designed. This is how you assign tasks to CPUs via dispatch queues that are basically run queues. You insert task into a queue, and the SCHEDX core will take care of dispatching task on the CPU. So there's a local, the SCX DSQ local is a keyword that represents a DSQ on each CPU. If you dispatch task using DSQ local, it will be added to the run queue of the CPU assigned to the task. But you can also migrate task by sending them on a diff queue, doing this, SCX DSQ local on and the CPU number. Or there's also a global DSQ. These are all built-in queues that you can use in your scheduler. The global one just consumed in FIFO mode from all the CPUs, whereas these ones will be consumed only by the specific CPU. So we have the concept of local queues and global queues. In addition to that, you can create user-defined DSQs. So if you create your own DSQ, you can decide which CPU is allowed to consume from that. And you can use user-defined DSQs to implement, for example, per LLC queues, or per NUMA node queues, or per scheduler domain queues, and whatnot. And so here's the workflow. Tasks from, once you insert a task in the local DSQ, it will be automatically consumed by the kernel SCHEDX logic and will dispatch the task on the target CPU. If the local DSQ is empty, the core, in-kernel core, will check if there's any task in the global DSQ and move the first guy from here to here, or, I mean, the first CPU that is available. And then, again, the same logic triggers, so the first task from the DSQ is consumed and moved to the CPU. If there's no task in the local DSQ and no task in the global DSQ, a callback called dispatch will be invoked, and if you implement this in your scheduler, you can decide what kind of logic you want to use in the dispatch ops. And in the dispatch ops, usually you consume from user DSQs. And you can use this SCX BPF DSQ move to local to pick the first guy from here and move into a local DSQ. And dispatch, if you use this, dispatch will move the task, of course, in the current CPU, the local DSQ of the current CPU. So in this way, it's how you assign tasks to CPUs. The DSQs are, so the built-in one, the global DSQ, local DSQ, they can only work in FIFO mode, while the user DSQ can work both in a FIFO mode or in a priority mode. And the priority mode is called, let me see if I have the exactly. If you run SEX BPF DSQ insert, it would insert a task into a DSQ and consume that in FIFO mode. And insert vtime, remember vruntime? Insert vtime is the priority one, and in the backend it would use an RB3 to sort tasks by the value that you can specify a value, and that would represent like the order, the place inside the queue for the task. And if you pass the vruntime, basically you can implement the CFS, completely fair share scheduler, using this one, and maybe a global DSQ with using the vruntime. You can't use FIFO and vruntime for a user DSQ at the same time. It's either one or the other. They're mutually exclusive. But yeah, that's an important concept that I wanted to mention, just in case you want to start playing with that, because it's documented, but it's kind of tricky to understand. Let's go to another question. Evans, how weight is measured? So weight is derived from the nice value. There's a logic, like it uses a logic in the kernel to translate the nice level into a weight that goes from 1 to 10,000. That's the scale. And the default value is 100, because it's just traditionally it's how. So the same logic is in C group. If you go into the C group CPU weight, that's the same logic. Like you find the same logic both in C group CPU weights and in SCADX priority or SCADX weights. And you can access the weight like if you, yeah, I didn't mention, but this is for example, it's a scheduler. You implement all these callbacks, and for example, in queue is when a task wants to run. Dispatch, it's when a CPU is available. Runnable is when a task becomes ready to run. And then we have running when it actually starts to run. Stopping when it stops to run because it either expires its time slice or because it's blocking on an event. And quiescent, for example, it's when it's blocking on an event. And if it goes here and it receives a wake up event, we will go back to the beginning where we can, on wake up, we can select a new CPU potentially, and queue, dispatch, runnable, running, and so on and so on. And then we have an exit. Yeah, we also have, here's the complete workflow that explains, like this is not documented. So if you have this, maybe we can upload the slides somewhere, and that would be nice, but we will document this one. This is like how all the callbacks that you can implement for regarding the task workflow. Let me see, another question. Is it easy to switch from one version of the scheduler to another, or it requires system and kernel programming expertise? Well, switching from one scheduler to another is like, I was doing, okay, let's see. Let's do a demo. Actually, let's generate, okay, this one is cool. There's a fish tank, you see the same FPS. Let's try 2 different schedulers. Maybe while I recompile the kernel, how about that? So I'm recompiling the kernel, I'm doing 7 FPS, that's not great. Let's go to SCX simple. So SCX simple is a vruntime based scheduler. Yeah, you see, it's not improving much. It's actually worse, because EVDF is better in terms of latency than a completely fair share scheduler, right? So I stop this and I'm back to the default scheduler. And okay, thanks, Candice. And then if I do like SCX bidder, this one is another scheduler. This one is prioritizing latency sensitive tasks a lot. And you can see now the FPS, not here, but FPS here is much higher. So this is how you switch from a scheduler to another, or you can do, for example, I can go with a Rust. This is the Rustland. This is the full user space scheduler, for example. And it's actually performing really well in this case. You see, it's actually doing better than the previous one. Or I can switch to BPF land. This is another scheduler. LAVD. This is the gaming scheduler. So you see, it's really easy to switch from one scheduler to another. And I was doing that while recompiling the kernel. So I think that's very powerful. Okay, let me. Yeah, like I mentioned, there's you need the kernel and the SCX repo to play with SCADX. But let me go to the final slide, and then we keep some time for the last questions. So one thing that I would like to improve is scheduler's composability, because right now we allow to load only one scheduler at a time. And it would be nice to have the possibility to say, you have multiple C groups, attach a separate scheduler per C group. And a lot of people are asking for this feature, which is, I'm not a big fan of adding that, because in my opinion, we could implement this by providing a better scheduler composability. With composability, I mean, let's assume the schedulers are like libraries, So you can say, if a task is running in this C group, use this scheduler. If another task is running on another C group, use this other scheduler, where schedulers are like libraries, and you import the libraries in your project. Or even more than that, like having much more granularity for libraries. Let's say I want to use the load balancer from Rusty and the CPU idle selection policy from BPF land, and maybe the scheduling from LAVD. I like the building blocks. So I put all the building blocks together and I make my own scheduler, or I make a meta scheduler that implements different scheduling policies based on C groups, for example, using these building blocks. I think something like that would be a lot more powerful, and basically would allow to implement the second point here, like the possibility to load multiple SCX schedulers at the same time. Of course, you are working, like the development is really still active. I mean, it has been merged, but that doesn't mean that the project is over. There's so many that, like, we keep improving things like the built-in functionalities. For example, right now I'm working on a patch to make the built-in idle tracking like per NUMA. So it would improve to improve this logic for big machines with multiple NUMA nodes. We're working to provide more in kernel statistics. And yeah, one of the interesting things to explore is paravirtualization scheduling or cooperative scheduling, like scheduling based on ints from guests, for example. So find a way to communicate from the guest scheduler to the host scheduler so that the host scheduler can take better scheduling decisions. I think that would be a really nice field to explore. And there's a lot of potential for improvement. See that I left some references here, and we go to questions. Last questions. I mean, whatever we have. Is it possible to have nested scheduler like inside? Yeah, exactly. That's exactly what I was saying. Like right now, it's not possible because we allow to load only a single scheduler. Each like you can't have two SCADX schedulers running at the same time. But you can already implement a scheduler that has like a logic inside that says, if a task belongs to a specific container, apply this particular scheduling policy. Otherwise, if a task belongs to a different container, use a different scheduling policy. And within BPF, you have access to the C groups using either the BPF APIs or the SCADX APIs. So you already have this possibility. I mean, we don't have a scheduler right now that does that, but with a better scheduling composability, I think we can improve this a lot. Like, and we can have ways we can have tools to attack and approach this problem of having like multiple schedulers per container or per VMs, let's say. Other questions that I may have missed?
I answered one question, Andre, on maybe you can add to it. In the default schedules, are the tasks assigned the same priority and time slice? I mean, you can tweak priorities using NICE and sysctl. Timing, I think, is the same. Time slice, I don't think can be adjusted. So that is the one question I answered.
Yeah, exactly. That's correct. So in and the thing is like, so with the something to notice is that the EVDF uses the deadline is based on the time slice. So that's another caveat sometimes about the EVDF. Usually we have found that it seems better to evaluate the deadline like by keeping track of how much time a task is using. For example, the Vader scheduler that I showed, it's evaluating the time slice using the vruntime, and instead of adding the scaled supposedly requested time slice, it measures the time from when the task becomes runnable up to when the task releases the CPU. So what it does, let's say you have a CPU intensive task, it would have this partial runtime that would grow bigger and bigger. So its deadline would be delayed a lot. And if you have a task that is sleeping often and it's constantly releasing the CPU, it would have the partial vruntime really small. That value is added to the vruntime. So the consequence is that latency sensitive task will automatically have a shorter deadline. So they will get more chances to run. And another cool thing that you can do in SCADX, you can explicitly assign the time slice for each task when you dispatch or when you enqueue a task. Or when you move a task actually to a DSQ. So that means you can do interesting tricks, like let's say if you have a single global queue that is growing too long, like tasks are piling up, you can basically assign time slice as like inversely proportional to the amount of tasks that are sleeping. This is another trick that works really well for because in this way you will have more context switches, but task will get more chances to run because they have a shorter time slice. So you basically reduce the average wait time in this way. And it's really simple. With this logic, like a FIFO scheduler sometimes performs better than EVDF just by implementing this little trick.
There's one more follow-up question about time slice, whether it's static or dynamic in the Q&A.
Oh, in the Q&A, let me see. Is time slice static or dynamic? So you can, let me see, what you can do. I'll show the code so that it's easy to understand. Let's say, okay, Vader, this is the scheduler. So this is actually a good scheduler if you want to learn about SCADX. I mean, it's good, not good in terms. It's also a nice scheduler, but it's good because I put a lot of comments in here, and you can find this on the SCX repo. So, for example, if I go in and queue right here. You see, so this is how I enqueue a task in a shared DSQ. This scheduler is using a single global custom DSQ called shared DSQ. You see that I assign a slice that I determine as task slice, which is basically, like I said, it's the default slice that is 20 milliseconds. And they divide that by the amount of tasks that are waiting in the global DSQ. So it is when a task is starts to run, this is the budget of the time slice budget that the task has. But anytime, either in opstick or in any other callback, if you can change the slice, you can like reset the slice to 0, and the task basically would be preempted. This is how preemption can be implemented. So the time slice is dynamic, I would say, because you can change it any time. You can assign a predefined value or have defaults or whatnot, but you can constantly change and adjust the time slice in your scheduler simply by either when you insert a task into DSQ, or you can do for example, here you can do this is a task struct. If you do pointer SCX slice equal time slice, here I'm refilling the time slice. Basically, this is in this patch. I'm saying if there's someone that is ready to run in this CPU, just consume the task from the shared DSQ and go. But otherwise, if no one else wants to go, and prev, the previous task in this CPU still wants to run, just refill its time slice. So this is an optimization, right? It's commented here, like if the current task expired its time slice and no other tasks want to run on the CPU, replenish its time slice and let it run for another round on the same CPU. So this is like another optimization that, because otherwise I can save some callbacks by doing so. So I hope this answered your question.
See, I have a question, Andrea. So I often run 6 compiles at once. Would that workload be conducive to SCADAX? And I could, so if I played with it, I could reduce my compile
time? So yes, the short answer, yes.
Yes.
So you can do 2 things. So if you run this scheduler right here, the Vader scheduler,
right,
it would actually, so if you run these and other things in your system, like I'm doing, I'm compiling the kernel while I am, I don't know, watching a video on YouTube or doing the live stream, for example. If I do that, your kernel build would be slowed down because it gives, the latency sensitive task gets more priority. But let's say if you are on a build server and you only have the kernel build running,
right?
So one thing that I found that can help to make the build faster is to use a shared DSQ like I'm doing here.
Okay.
So basically, this scheduler without the logic of prioritizing latency sensitive tasks. And I've actually done some experiments inside NVIDIA for builders, and we were able. So in one case, there was an Intel machine with NUMA nodes, so we can also do some tricks for the topology. We were able to speed up the kernel build by 10-15%, which is a lot. Like I was actually impressed. But that's because on that particular architecture, because it's quite an old Intel that is very susceptible to cache coherency. So if you pack tasks together into NUMA nodes, it works better. Let's say on a system without doing these NUMA tricks, like on a plain system where all the CPUs
plain system
in the same plain system, I was able to get like 4 or 5% speed up by using a shared queue.
Okay.
And this happens because like EVDF or the Linux scheduler, it's using a queue for a run queue per CPU, and then there's the load balancer. So that means, you know, the math theory tells us that if you have multiple servers, using a single queue is more efficient than using a queue per server. You know, you go to the grocery store, it would be better if you could, you know, get to the first checkout that is available, right? Instead of waiting on one. So why is Linux doing that? Like why there's a per CPU queue? And well, for multiple reasons. One of them is that context switches, for example, are faster because you don't have to do migration.
Right.
And the other thing is cache coherency is better used because you're more likely to remain, a little bit more likely to remain on the same CPU before migrating. You migrate only when the load balancer decides to do so. And but in specific works like a builder, for example, you don't get much benefit for cache locality because you just produce the object file and you throw away everything. So it is actually better to get rid of the per CPU queues and use a shared one because it can improve the overall core utilization. And yeah, that's a technique that is a lot effective. And there's actually in BPF land, I added an option to do that. So you can run BPF land -p that is like, it makes your scheduler good for builders.
Okay, sounds great. So it looks like we're almost out of time. Candice, how are we doing on time?
We're a little bit over, but if there are any last questions, we can definitely finish those up.
Looks like there is one question about time slice, time slice in Q&A. I think that might be the last question, really. I don't think we have any more.
So small time slice can cause thrashing. Yes, that's correct. If you reduce the time slice, you increase the amount of context switches. So more overhead for the system. So yeah, that's correct. Yeah, it's always difficult to find the right balance, you know, for having a good time slice. But yeah, it's up to the scheduler logic to decide like how much you want to assign to each task. There's another one. Since you work with NVIDIA, I assume you are very well tuned schedulers, machine learning, especially since the tasks are homogeneous. Am I correct? So honestly, I don't know very much about machine learning. I'm more of a kernel guy. So yeah, I'm trying to I know who to ask. But like I said earlier, I think we're far from having like an AI that is able to design a good scheduler. What we can do, and I say that already, what we can do maybe is to generate more data, like generate traces and feed an AI with this data and maybe get something. But I mean, we don't have a magic wand and say, hey, hi, the design the best scheduler ever. It produces poor results if you try to do that, at least in my experience.
Yeah, almost 5 minutes over. We have a couple of people with their hand raised. I don't know if you have any question. There is one question about, would work stealing be a good idea between the per CPU queues? I think that is the very last question we'll take.
Yeah. So yeah, that's work stealing is, you know, if you anything that makes your scheduler more work conserving, like either by by using a single global run queue, or be more aggressive at load balancing, helps for the builder's workload, like, you know, having doing massive parallel builds. Of course, if you can maximize the core usage, it helps. But again, you find something that seems to work really well for your use case. It's difficult to upstream that. So now we can use that because we have SCADX. So you say, you know, for a builder, it works. It's better to have a single shared DSQ then fine, let's do that in BPF. Let's do that with SCADX. And so that's why at the beginning I said I feel like there are many low-hanging fruits that we can get by using specialized schedulers. So yeah, all those things like work stealing, would work stealing be a good idea? All those answers, you can get all those questions. You can get an answer quickly by testing that in SCADX. And if you find something that works and it's not regressing other workloads, we can upstream that. That could be a good contribution for the default scheduler.
Thank you, Andre. I'll kick this back to Candice to close us out.
Thank you so much, Andre and Shiro, for your time today. And thank you, everyone, for joining us. As a reminder, this recording will be on the Linux Foundation's YouTube page later today, and a copy of the presentation slides will be added to the Linux Foundation website. We hope you're able to join us for future mentorship sessions. Have a wonderful day.